This video presents the results of the fit-for-purpose and mass migration threads of OGC Testbed 13. We'll cover three topics: the test scenario, the architecture, and the results. Our scenario recognizes that years of war have displaced hundreds of thousands of people from Dara, Syria to Zaatari, Jordan. In this scenario, a ceasefire has been declared, and government and non-governmental organizations need help in returning the displaced population. To do this, they need to access information for both Dara and Zaatari to assist in humanitarian relief. Our first set of users aren't experts and they don't know about satellite imagery or complex geospatial data sources. They just have questions, such as what's the safest route from Zaatari to Dara? Other users in our scenario are more sophisticated. They have visualization clients and simulated relief operations centers, field mobile clients, and they have the capacity to make information for others. These four types of users are shown at the top of the architecture: non-expert and expert clients, visualization clients, and mobile clients. These clients will be accessing a variety of OGC services. A key element of Fit for Purpose is developing and testing a simple way to access imagery metadata, create flexible queries, and developing something that has wide support in software. To do this, we started by using web feature services to query and discover imagery metadata and footprints, and then visualize that data and process it with other OGC services like web map servers and processing servers. Let's take a look at our first client, the non-expert user.
The solution and feature developed allow users who do not understand complex geospatial data sources to simply interact with the data using natural language by asking a simple question to the system, such as, "What is the fastest route out of the Zaatari refugee camp?" and get answers in an easy to understand form. The user is presented with a series of ranked results which can be simply assessed by reading the abstracts. Once the needed information is discovered, the user can retrieve all complex geospatial data sources and analytic processes by clicking the plus icon. All the web service requests are automatically made by the system, and the information needed to answer the user's question is displayed on the map.
Now let's look at the expert user.
The solution and feature developed allows geospatial data experts who can interpret and organize complex geospatial data sources to quickly respond to a variety of user requirements. An expert can search for specific web services such as WFS covering an area of interest. Visualize the content of the data. Apply a CQL filter to access only features with specific characteristics. The same CQL filter has been automatically applied to the related WMS service, displaying only the image that satisfies the filtering criteria. We can search for a web coverage service and dynamically access the data, which can be a subset, using, in this case, a lat-long filter. The geospatial data expert can make available to users a complex series of web services by creating an OWS context document with all the information needed to get the most of the data. including a web processing service with some analytical capabilities.
Next, let's take a look at the visualization user.
A user may want to visualize population and urban growth or decline within an area, as shown here with the temporal configuration of the nighttime imagery. We view changes before 2012 and after 2016. We now navigate to the Zatari area. Here we load a layer which contains temporal information. To load it, we select the desired time frame from start to end. Now we can enable the animation options at the top and visualize the changes through time. Panning and zooming are built-in visualization features which allow for user-friendly manipulation of the data. We can also visualize and obtain details about transportation resources, settlement fluctuations, and much more. Considering the sensitive nature of the information portrayed in many layers describing this region, web services can be provided in a secured manner. Here the user can access a service protected by OAuth 2.0. Users are expected to provide authentication details from the service providers to be able to load and analyze the content.
Finally, let's look at the field user.
Testbed 13 Task AB106 provides the fit-for-purpose thread, an Android and iOS compatible secure mobile client. Authorization and access support OAuth 2.0 with OpenID Connect. This technology is the same identity provider technology used by Google, Apple, and Facebook. We've used this technology in conjunction with other testbed participants to provide protected access to web map and web feature services. Additional to protected services, the mobile client is GeoPackage compatible, allowing workflow products exported as GeoPackage to be viewed in an online or offline state. The mobile client is capable of rendering imagery tiles, simple features, and feature collections, all from the GeoPackage.
Using the handset input sensors, such as the camera or microphone, we are able to capture field data and associate free text metadata or even provide structured metadata such as a form or questionnaire, all while associating this information with the logged-in user. All field captures are reviewable and can be visualized on the map alongside GeoPackage contents, WMS and WFS data. Handset captured data can be shared back to cloud services and disseminated to other web or mobile clients.
Collections of shared data that can be disseminated via GeoPackage or web services can be displayed alongside current data that's on the handset or cloud-based data, thus allowing a greater feedback loop from the workflow process and from data publishers or other clients.
Safe Software's FME is the data integration tool used to generate the OGC GeoPackage that supports the field client when offline. This data modeling workspace reads the project shapefile, clips by the DARA area, reprojects to the selected coordinate system, and writes out the results. It also reads recent satellite imagery from Sentinel-2, clips, reprojects, and writes this to a tile set within the same GeoPackage. The results can be previewed by FME Data Inspector before loading to the mobile client. Key to this is keeping the GeoPackage small and allowing updates to be easily automated so field operatives have access to the latest data.
It's important to remember that in this part of Testbed 13, a large amount of satellite imagery and other data was deployed, such as OpenStreetMap data in NGA formats, web feature services layers with imagery metadata, context documents, a large amount of satellite imagery data from Digital Globe and other providers. Some of the services were even secure, providing secure access to the imagery data. Finally, we saw processing services in action, where new row datasets were created over Zatari, bringing together more than one dataset to create a more complete dataset. This concludes our demonstration. Thank you.